All right, let's jump right in. We're about to take a look back at a proposal from 1999 that asked a really sharp question about how we teach physics. And you know what's wild? Is that this question is maybe even more relevant today. It's all about rethinking science education right from the very beginning. So, let's just start with the big one right here. When you think back to your first physics class, what comes to mind? Is it a lot of, blocks sliding down ramps and calculating the paths of cannonballs? Those things are classics for sure, but the argument here is that intro physics can often feel totally disconnected from all the mind-bending discoveries of the last century. Now, the solution being proposed isn't just, hey, let's cram more advanced stuff into the curriculum. No, it's something way more elegant. It's this idea called deep simplification. And the core of it is that the biggest breakthroughs in modern physics didn't just add complexity, they actually found a simpler, more powerful, and honestly, more beautiful way to explain how the universe works. And that really gets to the heart of the problem, doesn't it? The 20th century gave us absolute game changers like relativity and quantum mechanics, but the way we actually introduce students to physics, it's pretty much stayed the same. Our teaching methods just haven't kept up with our own scientific breakthroughs. And we need to be really clear about what deep simplification is. This is not about dumbing down physics. It's actually the complete opposite. It's about finding ways to teach that are more powerful, they explain more, and are also fundamentally easier for students to wrap their heads around. It's all about finding that elegant, simple truth at the core of a complex idea. The paper we're looking at points to thinkers like these guys as the absolute masters of this. You've got Minkowski, who turned Einstein's complicated math into simple geometry. You've got Richard Feynman, who made the weirdness of quantum mechanics into a process of just exploring every possible path. And Claude Shannon, who took simple statistics and created the foundation for our entire digital world. They all found a simpler, deeper way of seeing things. So, okay, that's the big idea. But what does it actually look like in a classroom? Well, let's take our first case study, and it's a big one. Einstein's theory of relativity. Probably one of the most intimidating topics for any new physics student. So on the left, you've got the traditional way, a wall of equations for things like time dilation and length contraction. It's super abstract and really tough to get an intuition for. But the new way, inspired by Minkowski, is totally different. It treats space-time kind of like a map. You use a single, simple equation to figure out the distance between events. It basically turns all that hard algebra into something you can visualize, like geometry. And the way you teach this is by completely flipping the script. Instead of just handing students the answers, you get them a set of data from a simulated experiment. You say, here's the time on the lab's clock, here's the time on the speeding glider's clock, and here's where it was. And then, you just let them play. You let them plot the numbers and hunt for the patterns themselves, to discover the rules of relativity on their own. And this quote right here, it just nails it. It's about letting students wrestle with the data. It's in that struggle, in that personal effort to make sense of it all, that you get that genuine aha moment. And that's an understanding that goes so much deeper than just memorizing a formula you were given. Okay, so this isn't just about relativity. This way of thinking can connect different areas of physics to totally modern fields and, get this, even let us actually see the invisible quantum world. For instance, take thermal physics. For a long time, it was kind of seen as a dead subject. But once you apply the statistical tools that people like Claude Shannon developed for information theory, it suddenly becomes this incredibly vital modern field. I mean, look at this. Its ideas connect directly to computer science, genetics, communication. It helps us understand complex systems from the information in our DNA to the data flowing through the internet. Now for a really cool little story. The paper talks about a physicist, Kevin Kautan, who was looking at these beautiful diffraction patterns. But he had a problem. He could see the amplitude of his data, the bright spots. But the other half of the information, the phase, was totally invisible to him. He called this problem his Fourier duck because he only had half the picture. And the solution he came up with was just beautiful. He figured out you could use a single pixel to represent the whole data point. The brightness of the pixel shows you the amplitude, how intense it is. And the color of that same pixel shows you the phase. Just like that, the invisible half of his data popped into existence, represented by color. And the power of a trick like that is it's huge. It takes these really complex ideas from quantum mechanics, stuff that used to only be accessible if you knew some seriously advanced math, and turns them into something you can literally see, something you can explore and build a real intuition for. It's a perfect example of deep simplification in action. So all of this sounds pretty great, right? More powerful, more intuitive, more engaging ways to teach science. Which, of course, brings us to the million-dollar question. If these better methods have been around for so long, why isn't every physics class taught this way?
Well, the source breaks down this kind of systemic inertia perfectly. For teachers who are already overworked, the simplest path is just to teach the same way they did last year. For a lot of students, memorizing a formula can feel a whole lot easier than what the paper calls intellectual pizzazz. And for textbook publishers, making a big change is a huge financial risk. You might tick off all the schools who are used to the old way of doing things.
So what you end up with is this big feedback loop. Publishers write the books based on how teachers teach teach based on what's in the books, and students just want to know what's on the test. The whole system is kind of locked in this cycle, and it makes real innovation incredibly difficult to pull off. And this brings us to our final and I think most important point. We really have to ask ourselves, what's the real cost of letting things stay the same? What do we, as a society, lose by keeping science education sort of frozen in time? I'll leave you with this last, really powerful question, taken straight from the source material itself. Because this isn't just some debate for academics. When we're facing huge challenges like global warming, and we have to make decisions about incredibly complex science, can we really afford to have a public whose basic understanding of physics hasn't been updated in more than 100 years? It's definitely something to think about.